Power factor. In electrical engineering, the power factor of an AC electrical power system is defined as the ratio of the real power absorbed by the load to the apparent power flowing in the circuit, and is a dimensionless number in the closed interval of -1 to 1. A power factor of less than 1 indicates the voltage and current are not in phase, reducing the instantaneous product of the two. Real power is the instantaneous product of voltage and current and represents the capacity of the electricity for performing work. Apparent power is the average product of current and voltage. Due to energy stored in the load and returned to the source, or due to a nonlinear load that distorts the wave shape of the current drawn from the source, the apparent power may be greater than the real power. A negative power factor occurs when the device generates power, which then flows back towards the source. In an electric power system, a load with a low power factor draws more current than a load with a high power factor for the same amount of useful power transferred. The higher currents increase the energy lost in the distribution system, and require larger wires and other equipment. Because of the costs of larger equipment and wasted energy, electrical utilities will usually charge a higher cost to industrial or commercial customers where here is a low power factor. Power factor correction increases the power factor of a load, improving efficiency for the distribution system to which it is attached. Linear loads with low power factor can be corrected with a passive network of capacitors or inductors. Nonlinear loads, such as rectifiers, distort the current drawn from the system. In such cases, active or passive power factor correction may be used to counteract distortion and raise the power factor. The devices for correction of the power factor may be at a central substation, spread out over a distribution system, or built into power-consuming equipment. In a purely resistive AC circuit, voltage and current waveforms are in step, changing polarity at the same instant in each cycle. All the power entering the load is consumed. Where reactive loads are present, such as with capacitors or inductors, energy storage in the loads results in a phase difference between the current and voltage waveforms. During each cycle of the AC voltage, extra energy, in addition to any energy consumed in the load, is temporarily stored in the load in electric or magnetic fields, and then returned to the power grid a fraction of the period later. Because high-voltage alternating current distribution systems are essentially quasi-linear circuit systems subject to continuous daily variation, there is a continuous ebb and flow of non-productive power. Non-productive power increases the current in the line, potentially to the point of failure. Thus, a circuit with a low power factor will use higher currents to transfer a given quantity of real power than a circuit with a high power factor. A linear load does not change the shape of the waveform of the current, but may change the relative timing between voltage and current. Electrical circuits containing dominantly resistive loads have a power factor of almost 1.0, but circuits containing inductive or capacitive loads can have a power factor well below 1. AC power flow has two components. These are combined to the complex power expressed volt-amperes. The magnitude of the complex power is the apparent power, also expressed in volt-amperes. The VA and bar are non-SI units mathematically identical to the watt, but are used in engineering practice instead of the watt to state what quantity is being expressed. The SI explicitly disallows using units for this purpose or as the only source of information about a physical quantity is used. The power factor is defined as the ratio of real power to apparent power. As power is transferred along a transmission line, it does not consist purely of real power that can do work once transferred to the load, but rather consists of a combination of real and reactive power, called apparent power. The power factor describes the amount of real power transmitted along a transmission line relative to the total apparent power flowing in the line. One can relate the various components of AC power by using the power triangle in vector space. Real power extends horizontally in the I circumflex direction as it represents a purely real component of AC power. Reactive power extends in the direction of J as it represents a purely imaginary component of AC power. Complex power represents a combination of both real and reactive power, and therefore can be calculated by using the vector sum of these two components. We can conclude that the mathematical relationship between these components is: as the power factor increases, the ratio of real power to apparent power increases and approaches unity, while the angle theta decreases and the reactive power decreases. As cos theta 1, its maximum possible value, theta 0 and so q0, as the load becomes less reactive and more purely resistive. As the power factor decreases, the ratio of real power to apparent power also decreases, as the angle theta increases and reactive power increases. There is also a difference between a lagging and leading power factor. The terms refer to whether the phase of the current is leading or lagging the phase-off voltage. A lagging power factor signifies that the load is inductive, as the load will consume reactive power, and therefore the reactive component formula _2 is positive as reactive power travels through the circuit and is consumed by the inductive load. A leading power factor signifies that the load is capacitive, as the load supplies reactive power, and therefore the reactive component formula _2 is negative as reactive power is being supplied to the circuit. If theta is the phase angle between the current and voltage, then the power factor is equal to the cosine of the angle, formula _8. Since the units are consistent, the power factor is by definition a dimensionless number between -1 and 1. When power factor is equal to 0, the energy flow is entirely reactive and stored energy in the load returns to the source on each cycle. When the power factor is 1, all the energy supplied by the source is consumed by the load. Power factors are usually stated as leading or lagging to show the sign of the phase angle. Capacitive loads are leading, and inductive loads are lagging. If a purely resistive load is connected to a power supply, current and voltage will change polarity in step, the power factor will be 1, and the electrical energy flows in a single direction across the network in each cycle. Inductive loads such as induction motors consume reactive power with current waveform lagging the voltage. Capacitive loads such as capacitor banks or buried cable generate reactive power with current phase leading the voltage. Both types of loads will absorb energy during part of the AC cycle, which is stored in the device's magnetic or electric field, only to return this energy back to the source during the rest of the cycle. For example, to get 1 kilowatt of real power, if the power factor is unity, 1 kV of apparent power needs to be transferred. At low values of power factor, more apparent power needs to be transferred to get the same real power. To get 1 kilowatt of real power at 0.2 power factor, 5 kV of apparent power needs to be transferred. This apparent power must be produced and transmitted to the load, and is subject to the losses in the production and transmission processes. Electrical loads consuming alternating current power consume both real power and reactive power. The vector sum of real and reactive power is the apparent power. The presence of reactive power causes the real power to be less than the apparent power, and so, the electric load has a power factor of less than 1. A negative power factor can result from returning power to the source, such as in the case of a building fitted with solar panels when surplus power is fed back into the supply. A high power factor is generally desirable in a power delivery system to reduce losses and improve voltage regulation at the load. Compensating elements near an electrical load will reduce the apparent power demand on the supply system. Power factor correction may be applied by an electric power transmission utility to improve the stability and efficiency of the network. Individual electrical customers who are charged by their utility for low power factor may install correction equipment to increase their power factor so as to reduce costs. Power factor correction brings the power factor of an AC power circuit closer to 1 by supplying or absorbing reactive power, adding capacitors or inductors that act to cancel the inductive or capacitive effects of the load, respectively. In the case of offsetting the inductive effect of motor loads, capacitors can be locally connected. These capacitors help to generate reactive power to meet the demand of the inductive loads. This will keep that reactive power from having to flow all the way from the utility generator to the load. In the electricity industry, inductors are said to consume reactive power and capacitors are said to supply it, even though reactive power is just energy moving back and forth on each AC cycle. The reactive elements in power factor correction devices can create voltage fluctuations and harmonic noise when switched on or off. They will supply or sink reactive power regardless of whether there is a corresponding load operating nearby, increasing the system's no-load losses. In the worst case, reactive elements can interact with the system and with each other to create resonant conditions, resulting in system instability and severe overvoltage fluctuations. As such, reactive elements cannot simply be applied without engineering analysis. An automatic power factor correction unit consists of a number of capacitors that are switched by means of contactors. These contactors are controlled by a regulator that measures power factor in an electrical network. Depending on the load and power factor of the network, the power factor controller will switch the necessary blocks of capacitors in steps to make sure the power factor stays above a selected value. Instead of using a set of switched capacitors, an unloaded synchronous motor can supply reactive power. The reactive power drawn by the synchronous motor is a function of its field excitation. This is referred to as a synchronous condenser. It is started and connected to the electrical network. It operates at a leading power factor and puts VARs onto the network as required to support a system's voltage or to maintain the system power factor at a specified level. The synchronous condenser's installation and operation are identical to large electric motors. Its principal advantage is the ease with which the amount of correction can be adjusted. It behaves like a variable capacitor. Unlike capacitors, the amount of reactive power supplied is proportional to voltage, not the square of voltage. This improves voltage stability on large networks. Synchronous condensers are often used in connection with high-voltage direct current transmission projects or in large industrial plants such as steel mills. For power factor correction of high-voltage power systems or large, fluctuating industrial loads, power electronic devices such as the static VAR compensator or STATCOM are increasingly used. These systems are able to compensate sudden changes of power factor much more rapidly than contactor-switched capacitor banks, and being solid-state require less maintenance than synchronous condensers. Examples of nonlinear loads on a power system are rectifiers, and arc discharge devices such as fluorescent lamps, electric welding machines, or arc furnaces. Because current in these systems is interrupted by a switching action, the current contains frequency components that are multiples of the power system frequency. Distortion power factor is a measure of how much the harmonic distortion of a load current decreases the average power transferred to the load. In linear circuits having only sinusoidal currents and voltages of one frequency, the power factor arises only from the difference in phase between the current and voltage. This is displacement power factor. Nonlinear loads change the shape of the current waveform from a sine wave to some other form. Nonlinear loads create harmonic currents in addition to the original AC current. This is of importance in practical power systems that contain nonlinear loads such as rectifiers, some forms of electric lighting, electric arc furnaces, welding equipment, switched-mode power supplies, variable speed drives and other devices. Filters consisting of linear capacitors and inductors can prevent harmonic currents from entering the supplying system. To measure the real power or reactive power, a wattmeter designed to work properly with non-sinusoidal currents must be used. The distortion power factor is the distortion component associated with the harmonic voltages and currents present in the system. Formula_11 is the total harmonic distortion of the load current. Formula_13 is the fundamental component of the current and Formula_14 is the total current. Both are root mean square values. This definition with respect to total harmonic distortion assumes that the voltage stays undistorted. This simplification is often a good approximation for stiff voltage sources. Total harmonic distortion of typical generators from current distortion in the network is on the order of 1 to 2%, which can have larger scale implications but can be ignored in common practice. The result when multiplied with a displacement power factor is the overall, true power factor or just power factor. In practice, the local effects of distortion current on devices in a three-phase distribution network rely on the magnitude of certain order harmonics rather than the total harmonic distortion. For example, the triplen, or zero sequence, harmonics have the property of being in phase when compared line to line. In a delta Y transformer, these harmonics can result in circulating currents in the delta windings and result in greater resistive heating. In a Y configuration of a transformer, triplen harmonics will not create these currents, but they will result in a non-zero current in the neutral wire. This could overload the neutral wire in some cases and create error in kilowatt-hour metering systems and billing revenue. The presence of current harmonics in a transformer also result in larger eddy currents in the magnetic core of the transformer. Eddy current losses generally increase as the square of the frequency, lowering the transformer's efficiency, dissipating additional heat, and reducing its service life. Negative sequence harmonics combine 120 degrees out of phase, similarly to the fundamental harmonic but in a reverse sequence. In generators and motors, these currents produce magnetic fields which oppose the rotation of the shaft and sometimes result in damaging mechanical vibrations. A particularly important class of nonlinear loads is the millions of personal computers that typically incorporate switched-mode power supplies with rated output power ranging from a few watts to more than 1 kilowatt. Historically, these very low-cost power supplies incorporated a simple full-wave rectifier that conducted only when the mains instantaneous voltage exceeded the voltage on the input capacitors. This leads to very high ratios of peak to average input current, which also lead to a low distortion power factor and potentially serious phase and neutral loading concerns. A typical switched-mode power supply first converts the AC mains to a DC bus by means of a bridge rectifier or a similar circuit. The output voltage is then derived from this DC bus. The problem with this is that the rectifier is a nonlinear device, so the input current is highly nonlinear. That means that the input current has energy at harmonics of the frequency of the voltage. This presents a particular problem for the power companies, because they cannot compensate for the harmonic current by adding simple capacitors or inductors, as they could for the reactive power drawn by a linear load. Many jurisdictions are beginning to legally require power factor correction for all power supplies above a certain power level. Regulatory agencies such as the EU have set harmonic limits as a method of improving power factor. Declining component cost has hastened implementation of two different methods. To comply with current EU standard EN 61032, all switched-mode power supplies with output power more than 75 W must include a passive power factor correction, at least. 80+ power supply certification requires a power factor of 0.9 or more. The simplest way to control the harmonic current is to use a filter that passes current only at line frequency. The filter consists of capacitors or inductors, and makes a nonlinear device look more like a linear load. An example of passive PFC is a valley fill circuit. A disadvantage of passive PFC is that it requires larger inductors or capacitors than an equivalent power-active PFC circuit. Also, in practice, passive PFC is often less effective at improving the power factor. Active PFC is the use of power electronics to change the waveform of current drawn by a load to improve the power factor. Some types of the active PFC are buck boost, and synchronous condenser. Active power factor correction can be single-stage or multi-stage. In the case of a switched-mode power supply, a boost converter is inserted between the bridge rectifier and the main input capacitors. The boost converter attempts to maintain a constant DC bus voltage on its output while drawing a current that is always in phase with and at the same frequency as the line voltage. Another switched-mode converter inside the power supply produces the desired output voltage from the DC bus. This approach requires additional semiconductor switches and control electronics, but permits cheaper and smaller passive components. It is frequently used in practice. For a three-phase SMPS, the Vienna rectifier configuration may be used to substantially improve the power factor. SMPSs with passive PFC can achieve power factor of about 0.7 to 0.75. SMPSs with active PFC, up to 0.99 power factor, while a SMPS without any power factor correction have a power factor of only about 0.55 to 0.65. Due to their very wide input voltage range, many power supplies with active PFC can automatically adjust to operate on AC power from about 100 V to 240 V. That feature is particularly welcome in power supplies for laptops. Dynamic power factor correction, sometimes referred to as real-time power factor correction, is used for electrical stabilization in cases of rapid load changes. DPFC is useful when standard power factor correction would cause over or under correction. DPFC uses semiconductor switches, typically thyristors, to quickly connect and disconnect capacitors or inductors to improve power factor. Power factors below 1.0 require utility to generate more than the minimum volt-amperes necessary to supply the real power. This increases generation and transmission costs. For example, if the load power factor were as low as 0.7, the apparent power would be 1.4 times the real power used by the load. Line current in the circuit would also be 1.4 times the current required at 1.0 power factor, so the losses in the circuit would be doubled. Alternatively, all components of the system such as generators, conductors, transformers, and switchgear would be increased in size to carry the extra current. When the power factor is close to unity, for the same kVA rating of the transformer more load can be connected. Utilities typically charge additional costs to commercial customers who have a power factor below some limit, which is typically 0.9 to 0.95. Engineers are often interested in the power factor of a load as one of the factors that affect the efficiency of power transmission. With the rising cost of energy and concerns over the efficient delivery of power, Active PFC has become more common in consumer electronics. Current Energy Star guidelines for computers call for a power factor of greater than or equal to 0.9 at 100% of rated output in the PC's power supply. According to a white paper authored by Intel and the U.S. Environmental Protection Agency, PCs with internal power supplies will require the use of active power factor correction to meet the Energy Star 5.0 program requirements for computers. In Europe, EN 61032 requires power factor correction be incorporated into consumer products. Small customers, such as households, are not usually charged for reactive power, and so power factor metering equipment for such customers will not be installed. The power factor in a single-phase circuit can be measured with the wattmeter-ammeter-voltmeter method, where the power in watts is divided by the product of measured voltage and current. The power factor of a balanced polyphase circuit is the same as that of uniphase. The power factor of an unbalanced polyphase circuit is not uniquely defined. A direct reading power factor meter can be made with a moving coil meter of the electrodynamic type, carrying two perpendicular coils on the moving part of the instrument. The field of the instrument is energized by the circuit current flow. The two moving coils, A and B, are connected in parallel with the circuit load. One coil, A, will be connected through a resistor and the second coil, B, through an inductor, so that the current in coil B is delayed with respect to current in A. At unity power factor, the current in A is in phase with the circuit current, and coil A provides maximum torque, driving the instrument pointer towards 1.0 mark on the scale. At zero power factor, the current in coil B is in phase with circuit current, and coil B provides torque to drive the pointer towards 0. At intermediate values of power factor, the torques provided by the two coils add and the pointer takes up intermediate positions. Another electromechanical instrument is the polarized vane type. In this instrument, a stationary field coil produces a rotating magnetic field, just like a polyphase motor. The field coils are connected either directly to polyphase voltage sources or to a phase-shifting reactor of a single-phase application. A second stationary field coil, perpendicular to the voltage coils, carries a current proportional to current in one phase of the circuit. The moving system of the instrument consists of two vanes that are magnetized by the current coil. In operation, the moving vanes take up a physical angle equivalent to the electrical angle between the voltage source and the current source. This type of instrument can be made to register for currents in both directions, giving a four-quadrant display of power factor or phase angle. Digital instruments exist that directly measure the time lag between voltage and current waveforms. Low-cost instruments of this type measure the peak of waveforms. More sophisticated versions measure the peak of the fundamental harmonic only, thus giving a more accurate reading for phase angle on distorted waveforms. Calculating power factor from voltage and current phases is only accurate if both waveforms are sinusoidal. Power quality analyzers, often referred to as power analyzers, make a digital recording of the voltage and current waveform and accurately calculate true power, apparent power factor, AC voltage, AC current, DC voltage, DC current, frequency, IEC 6100032 2/3-12 harmonic measurement, IEC 6100033 3/11 flicker measurement, individual phase voltages in delta applications where there is no neutral line, total harmonic distortion, phase and amplitude of individual voltage or current harmonics, etc. English language power engineering students are advised to remember, Eli the Iceman or Eli on ice, the voltage E leads the current I in an inductor L, the current leads the voltage in a capacitor C. Another common mnemonic is civil, in a capacitor the current leads voltage, voltage leads current in an inductor.